Hello and welcome to my YouTube channel. Today we shall be treating the topic metric/metric space. Definition. Metric. Let X be any non-empty set. A function d from the Cartesian product of x to the positive real numbers including 0 is said to be a metric on x if it satisfies the following conditions. Let us take a closer look again at what the Cartesian product is. If we have two sets, say A and B, A with elements 1, 2, 3, B with elements 4 and 5, then a pair 1, 4 will be called the cross product of set A and B. If the first element of the set belongs to the first set A and the second element 4 belongs to the second set B. So this pair is called an ordered pair for that reason. So another Cartesian product we can form from these two sets would be the pair, say 2, 5. Since 2 belongs to the first set A and 5 belongs to the second set B. The pair, however, 5, 2, would not be called a Cartesian product of set A and B because the first element of this pair belongs to the second set, while the second element belongs to the first set. So for a particular pair to be called a Cartesian product, the first element of that pair must belong to the first set, while the second element of the pair must belong to the second set. However, in our definition of a metric, the Cartesian product here happens between the same set, x and x. So we're looking at something like this. We have a set here, x, which is non-empty, and we have elements in that set, say x and y. So the Cartesian product here happens between these two elements within the same set. D here is a function which is called the distance function. And the codomain 0 and to infinity simply means that when the distance function acts between these two elements of this set, the distance between these two elements, d, must always be positive. Of course, 0 is inclusive. So this function we have defined for a metric is nothing but a function that measures the distance between 2 points, in a non-empty set X. So the function d here is nothing but the distance function. So such a function d that measures the distance between 2 points, in a non-empty set X would be called a metric on the set X if it satisfies the following 4 conditions. 1. The distance between the 2 points, x and y, is always positive. 2. The distance between the 2 points is 0, implying that x and y are the same. What are we saying? In fact, the first one is saying that the distance between the 2 points, between point x and point y, must be positive at all times. So there is no room for negative distance here. Which means that if d becomes a negative number, then this d will not be called a function or will not be called a metric, on the set X. The 2 is saying that if the distance between these 2 points, is 0, it will simply imply that the 2 points are the same. Which makes sense. Because if the 2 points are different, the distance cannot be 0. And of course, if the 2 points are the same, it will also imply that the distance between the 2 points is 0. So the implication here is by implication. It goes both ways. The third condition is that the distance between point x and point y should be the same as the distance between point y and point x. What does it mean? That if we measure the distance from point x to point y in this direction, the value should be the same as if we had measured from point y back to point x. And this is what we call the symmetric property. It's called the symmetric property. The symmetric property, or axiom if you want. Now the third axiom here is that the distance between point x and y should be less than or equal to the distance between point x and point z, and plus the distance between point z and point y. This one is simply saying that if we have 3 points, within our sets. In our sets, say set x has 3 points. The first point is point x, point y, and the third point is point z. What this is saying is that the distance from point x to y should be less than or equal to the distance from point x to point z plus the distance from point z to point y. And this is what we refer to as the triangle inequality. So we are saying that the distance function d must satisfy the triangle inequality 4. So, if the distance function d, so defined, satisfies the 4 conditions stated so far, we will now say that d qualifies to be called a metric on the non-empty set X. And if d is a metric on the non-empty set X, then the pair X and d is now called a metric space. Therefore, a metric space is simply a non-empty set with a metric d defined on it. We shall now take one example of a metric space just to clarify what we have said. Example: let R be the set of real numbers. Show that the function defined d, Cartesian product of R to R, defined by this, the distance between x and y is the absolute distance or the absolute value of x minus y for all xy in R. But to show that this distance function, defined as this, is actually a metric on R. Here, our Cartesian, product is R and R. So we are picking 2 elements from the same set, which is what? R. And the codomain is also R. To show this, we have to show that this function d satisfies the 4 conditions, that makes a metric on R. The first is that the distance between point x and point y, must be positive. So this distance dxy is nothing but what? The absolute value of x minus y. And if you pick any 2 numbers from R, say 1 and say 2, then the absolute value of 1 minus 2 is the absolute value of minus 1, which is equal to what? 1. And 1 is what? Greater than or equal to 0. So, number 1, the first condition is satisfied. That the distance between point x and point y, from this domain will always be positive. So, condition number 1 is ticked. The next condition, the second condition requires that the distance of x between x and y is 0, implies that x and y are equal. And if x and y are equal, it will also imply that the distance between x and y, is equal to 0. Now, what is the distance between x and y as defined here? Is the absolute value of x minus y. Okay, now this absolute value, if this absolute value is 0, it will imply that x minus y is 0. Because the absolute value of a number is 0 if the number itself is 0. So this will be 0 if x minus y is 0. And if x minus y is 0, it will also imply that x is equal to what? Y. So we have seen now that if the absolute value of x minus y is 0, it will imply that x is equal to y. And of course, if x is equal to y, it will also imply that x minus y is 0. And if x minus y is 0, it will also imply that the absolute value of x minus y is 0. So condition 2 is also what? Verified. The third condition requires that the distance function must be symmetric. That is, the distance between point x and y should be the same as the distance between point y and x. So, dxy, the distance between point x and y, is the absolute value of x minus y. We can rewrite this as the absolute value of negative what? Y minus x. So that minus times y is minus y, and minus times minus x is plus x. So we are okay. Using our absolute value properties, we can write this as the absolute value of negative 1 times the absolute value of y minus x. And of course, the absolute value of negative 1 is 1 times the absolute value of y minus x. And this is nothing but what? The absolute value of y minus x. And the absolute value of y minus x is nothing but the distance between point y and point x. So we have shown that the distance dxy is the same as the distance what? Dyx. Meaning that the distance function as defined here is symmetric. So condition number 3 is satisfied. We are now left to show that condition number 4, the triangle inequality, also holds. So to show that the distance between point x and y is less than or equal to the sum of the distances between point x and point z and point y. So dxy simply means what? X minus y. I can rewrite this as x minus z plus z minus y. I've only introduced a convenient 0 here, since minus z plus z is 0. So what I have on the right hand side is the same as what I have on the left hand side. I can rewrite what I have here as x minus z plus z minus y, still in absolute values. Now from our absolute value properties, we can write this absolute value to be less than or equal to the absolute value of x minus z plus the absolute value of what? Z minus y. This is less than or equal to the absolute value of x minus z is simply the distance between point x and point z, plus the absolute value of z minus y simply means the distance between point what? Z and point y. So we have just shown that the distance between point x and point y is indeed less than or equal to the sum of these two distances. So the fourth condition of triangle inequality also has been satisfied. Since the distance function d, defined as the absolute value of x minus y for all x and y in R, satisfies the four conditions that makes the distance function a metric, we now conclude that indeed this distance function d is a metric on the set R of all what? Real numbers. And of course, the pair x and R can now be called a metric space. Kindly subscribe to this YouTube channel if you have not done so already, and share, like, and leave a comment. Thank you for now, and bye-bye.